I hope the record is now on. Okay. Uh, okay. The record is now on. So let me tell you that this is the last chapter, and generally we may be able to finish this even before 3 hours. I'd like you to know that this is quite an easy subject. So if your mind is positive, I think we can be just fine with it. And yes, the topic is about the influence line, but it is going to be for the indeterminate structure. Okay, and for the academic purposes, I will only demonstrate in this class the indeterminate structure with 1 degree of redundancy. That would be more than enough. Okay, because actually when you go out in the real world, some computer programs are more than capable of creating the inference line of the indeterminate structures for you in like 2 seconds. So you need to know what you should be able to expect if you use computer programs and so and so. Okay. Before that, let me scroll back. This is the handout of the class. Okay. We in the previous class we discussed about Muller-Breslau principle. Okay, and we know that if a function at a point on the beam is allowed to act without restraint, the deflected shape of the beam will represent the inference line of the function. But of course, we will know only the shape. So this is a quick review of Muller-Breslau to get you into the gear. Okay, so let's say if you want to know the influence line of the reaction, okay, let's say this is the reaction. You will allow this reaction to travel freely by unlocking the vertical restraint, right? So when this reaction is allowed to move freely, it will push this beam upward because there is no vertical restraint. I should change the color. This beam will be pushed up freely like that, okay? Or I can just redraw this. You can see better. That there's a hinge there. And then this reaction move freely, so it pushes your beam up. So of course, that becomes the shape of the influence line of the reaction. Okay. Oh, sorry. Okay. Okay, let's say, well, naturally, we should name this A and B, right? So this is the shape of the influence line of reaction at B, because this is the deflected shape of your beam once the reaction at B is allowed to move freely. We don't only know the shape, but because we apply the unit load, so by more knowledge, you will know that this magnitude is going to be equal to what? Okay. And next is, say this is the reaction, right? So let me also write in front here that this is the reaction. Okay, what about the shear? The shear, well, you should, it's off. Yeah, maybe I'll try to realign this better. Okay. For the shear, we should know that the positive shear is like this. The side of the positive shear is going up on the left, going down on the right. So if I do this and I allow shear anywhere to go freely, you can look at this small piece here, and you see that you allow this going up on the left to go freely and going down the right to go freely. That means your free body diagram would be so that the shear on the left portion of this beam will have to go down to complete our equilibrium, correct? And on the right, the shear will have to go up to complete our equilibrium. Or you can just say, if you look at the left piece, you know, the shear is on the right, so it has to come down because on the right, downward shear is a positive one, right? So that means as a result, this will have to come down. And if you look at the piece on the right, this piece, because shear is now on the left, see, like this one, so it has to go up. So here, for this piece, it has to go up, and so it moves like that. Okay, so this is the shape. Okay, and that becomes the shape of the influence line of shear at any location. And now, because you know only the shape, if you want to have the number, you're going to have to use your engineering knowledge. And you will know because we use the unit load. So that means this distance will have to be equal to 1, right? And now you can use the similar triangle to determine how much this and that ordinate are going to be. Okay. The last one is the moment. Well, the moment, we will allow moment to go free, right? So let's say if there is a dot like that, you know, the sign of positive moment is smiling like that, right? And yes, you may guess now that if we want the moment to go free, we will add a hinge. And just like the shear before, you know, the positive side of the moment, you can look at this positive side and apply it right away, like this. And because we need to have equilibrium, that means on the left side, the moment will have to go like that. Oops, sorry. If we have to go like that to maintain equilibrium, and on the right side, you will have to go like that to maintain equilibrium. Or you can just say, okay, when you look at the left portion, it's this one, right? And when you look at the right portion, it's that one. So you can apply either way. And when you have that, what's going to happen to our structure is this. It's just going to go up like that, okay? Or I can just redraw it here. All right. And this will become the shape of the influence line of the moment. Okay, it doesn't look good. I try to find the better posture in drawing. Okay, so that's the influence line of the moment. And here would be the most common mistakes that the students generally make. Because if you want to know the magnitude of the influence line of the moment, they always think about the unit load. But what they don't think is that this, by the meaning of the influence line, this would be the magnitude of the moment right here, where the unit load is at that location of the beam, right? So if you want to calculate the moment, you're just gonna have to apply the unit load at that location. And this is, of course, this number is the magnitude of moment caused by unit load at the location. All right. So that should refresh our memories about the influence line. Is there any question? Would you like to see more example?
Yes.
Huh?
Yes.
Is it a yes? Okay. I thought so, you know. I shouldn't have asked, right? So I think I will put the example in front of this one so that when I turn this to PDF file, you can see the example as well, okay? So you find your own place to you know what? Okay, fine. No. No. I don't want it here. What do I do? You know what? Why can't I do anything about it? I should be able to erase this, right? Before. Okay, like that. Okay, let's see. I have an example around here. It's going to be quite difficult to open this up. So hang on. Okay, it may help, it may not help in the indeterminate structure, but let's have it. Okay. Let's say I have a B. Okay, because I have this 1, 2, 3, 1, 2, 4, 5, 6, like that. Okay. If there is a problem with the transmission of the signal, do let me know right away. Okay. Okay, this is the beam. And we have a point A right in the middle of this. This is point A, this is B, and this is C. This is 1.5 meters. This is another 1.5 meters. I can write better. You know what? Hang on. I don't know why I have a tendency to turn towards the monitor, which I don't really have to, right? Okay. So this is 1.5 meter. This is 1.5 meters. This is going to be 6 meters. Okay, and we'll try to use Muller-Breslau to obtain the, say, reactions. VA. Let's skip the added support because it's kind of tough to understand and it's just not gonna help with the inference line of the indeterminate structure. So let's go for this. Okay. So now we are, you guys are following up. You need a minute to catch up. The ones answering. Well, I'm used to that. So let's go for RB. Okay. For RB, of course, will allow the reaction at B to move freely. So as a result, the reaction at B here will push the entire beam to go up, right? And now you see that the shape of the inference line should become something like this. Yeah, you know what? Okay. And this is where B is, right? B pushes up the entire beam. And we know this is going to be the shape of our influence line. And we know that the reaction at B will have to be equal to 1 when you apply the unit load at B. So this height will be equal to 1. Okay. And so you can use the similar triangle to calculate this height. this height is going to be 1 divided by 6 multiplied by 9, correct? So it's 1.5. So that's the influence line of reaction at B for you. Okay, or I can just rewrite this for clarity. Okay, this is 1.5, and at the location B itself, this has to be 1, and this is the influence line of RB. Okay, next is RC. Okay, am I going too quickly? Anyone? Hello? Nobody's complaining. Okay, please let me know if this is too quick. Okay, now for the reaction at C, we will do the same again. We will try to let RC travel freely. So you have a hinge here and RC will go up freely. So the thing that will happen is that this will go up like a seesaw like that. Okay, so yeah, now we are going to have the shape of the influence line that looks like that. Okay, and at B will have to be 0 because that one got stuck, right? So our datum line is here. And we all know that when you apply the unit load at C, reaction at C will have to be 1. So by engineering knowledge, we know this is 1. And by similar triangle, we know this is 0.5, right? So I can, I forgot to say this is RC. So I can say, redraw this for clarity again. Okay. This is 1, this is minus 0.5, and this is, of course, the influence line of reaction at C. Okay? You know what? The internet here at home is way, way better. Now the at A, okay? I'm just gonna have to allow the shear at A to go freely. Okay, how do I do that? I will say impose a sort of a roller like this, so that the shear here can move freely. Okay, so it's up and down, and so this is down and up. So as a result, you know, when you look at the left side, if you want this piece on the left side, this piece to go freely, goes down, the entire piece will drop down, right? But on the right side, you have the entire beam in place, you know, with the hinge and the roller still there. So if you wish for this to go up, it can, right? You can't just push the beam up because it has 2 vertical reactions. So you can just say this will not, oops. This will not move. But this will move down freely. So that means your shape is going to look something like this guy will fall down freely, but on the right side, nothing moves. So that means the influence line of the shear at A will only look like this. And that is -1. Oh, look, that look like -1 at all. -1. Okay, and this is the influence line of VA. And it makes perfect sense, right? Because when you go back and look at this beam, you see the only way for you to have a shear at A is when the load is traveling around the left side of A. If you apply the load here, this load will not shear this part off, right? The only way that part A can be sheared off this structure is when there is an existence of load somewhere on the left side of it. Once the load travels over part A to somewhere, beyond A, before B, or after B, around here, the presence of the load on the right side will not shear part A off, right? And this is what I like to call talk to the structure. Okay, if you can see how the load is going to affect your structure, that is talking to the structure. Okay, now MA. Let's see if I can fit this in. Well, you know what? This is VA, right? MA. Well, in quite a rather similar fashion, when you apply the hinge at A, the structure on the right side again remains intact, right? So when you want to rotate this, again, this part will not rotate. Erase that a bit. My Y is too long. See, you can see the right part cannot rotate, right? However, the left part with that orientation will rotate freely. So that means the influence line of moment at A will look like this. This is point A, right? This entire thing will just come down. And this is the influence line of MA. And how much is this magnitude? Well, you're just going to have to apply the unit load at the location to see how much the moment is, right? And this is, the magnitude is moment at A when the unit load is applied at the tip, right? And when you apply the unit load at the tip, the moment at A is minus 1.5, right? Because that's the distance. So this is minus 1.5. Okay. And we run out of a piece of paper here, so I'm just going to add another one. Okay. When you look at the moment at the support, it is a similar thing. Okay. We have the support here. So we will add a hinge here. Again, now the hinge is on top of the support. So when you apply the moment, like this and that, actually, you know what? Let me try to, the moment here should be on the right side of the hinge, right? Right, correctly. Okay, that's more like it. Now let us go back here. When you see this, when you apply this moment here, again, the right side, your structure is intact. So you can't rotate it. So the result is similar. This portion will not rotate. And the portion on the right will again rotate freely. Okay, so that is a moment at C to you. And again, that means I can draw the influence line. And the shape will be just like that. And again, this is -3, right? Now you can guess this is the moment. Sorry, this is supposed to be at B, right? Moment at B when the unit load is applied at the tip. And the tip, the distance from the tip to the support is 3 meters. So this is -3. Okay, so that's Buller-Breslau with the help of your engineering knowledge, say equilibrium and so. Now we can have the influence line for everything. Okay, so that's the influence line in CVE 337 in a nutshell. Is there any question? Is there anything you'd like me to go over? Hello?
No question, Ajahn.
No question. Thank you. Thank you that you let me hear your voice. Anyone, someone. At least I know that I'm not crazily talking to myself at home. Okay. So I think that is the influence line, but it unfortunately for the determinate structure. So we need to go back to our class note and let's talk about the indeterminate structure a bit. I used to have the topic about the influence line in the truss, but I don't think it is very useful because in the end, it turns out to be just the magnitude of the axial forces, right? And so I have skipped over this part in the past few years, and I would likely to skip over this part again this year, unless, of course, someone wants to know about it. So let's hit the topic right away, the influence line for the indeterminate structure. Here we go. Okay. So as it says on the note here that influence line of the indeterminate structure is most conveniently obtained by starting off with the influence line of redundance first. Okay. So let's say we have the beam with 1 degree of redundancy here. So I think the first sensible and reasonable step is just to try to turn this into a determinate structure, right? So that we can deal with it. Okay, so for me, I prefer to remove the reaction in the middle. So let's again call this A, B, and C. So I am going to turn this indeterminate structure into a determinate one by removing the RB. Okay, so once I remove RB, it means that I have a structure that looks like this. Correct? Okay. So, well, the influence line is that, well, you need to apply the unit load. All right. Anywhere on the structure so that, well, you can calculate the reaction at B. Okay. So let's say the common nomenclature is that, let's say if I have the unit load here, and this is applied at the distance X. Okay. Now, your beam would form like that. Okay. And we will have deformation. Let's call this delta B. Okay. But to be more specific, I don't recall at all whether or not I have talked about this, but delta B here can be more specifically called delta Bx. Why do we call delta Bx? Because this means, let me try to put it somewhere here. Delta Bx, this is referred to displacement at B caused by load at X, right? And so let's say if I continue to move this unit load up until when it reaches B itself. When your unit load is at location B, we can readily call this displacement delta BB, right? Because the location of the load happens to be at B. Okay. It is explained down here that okay, be known as delta Bx. Okay. Now, okay, that's too far. And one more thing I'd like to tell you is that, so from this nomenclature, if I have the beam and I apply, let's say the load is at B. Oops, sorry. If the unit load is at B, let's say this is point B. And this is, remember this point X from the first picture. Let's say if this is point X, okay, same as that X. By nomenclature, I can call this delta XB, right? Displacement at X caused by load at B. Are you confused by the nomenclature? Hello? We are okay, right? You guys?
Yes, อาจารย์
Speak up, please. Don't be shy. You said yes, right? Didn't you?
Yes.
Okay, so we are good. Now, before I dive deeper into this, I'd like to show you this. Let's say if we use Muller-Breslau, okay? Now we're removing redundant B, right? So at least when you look at this indeterminate structure, if you are going to use Muller-Breslau, you allow reaction at B to go free, and the shape, the deflected shape of your beam will be the shape of the influence line of that reaction, correct? So in this case, if I allow RB to move freely, what would be the shape of the influence line of RB? I'd like to give you guys a minute or so to use your imagination what it would look like, and then I will draw it for you. What would be the shape of the influence line of RB and RA and then RC? I'll give you a minute to try to draw it in your own paper and see if your drawing will look similar to what I am going to draw in the next minute. Please go ahead, just for a minute, try to imagine what's going to happen. How would I know it's 1 minute? Okay, that should be about 1 minute, right? So let's say if I allow RB to move freely, the shape of the influence line of RB should look like this, right? RA and RC will be in place. So reaction at B pushes up. Now, because you have the two supports intact, so the deflected shape of RB will look just like, you know, the deformed shape of a simple B, like that. Do you have the same as mine? Hello? And you bet the magnitude here would have to be equal to 1. So that at least we know the shape of the influence line of RB, right? And what about, say, RC? Well, you want RC to move freely, so we have RA and RB intact. You allow RB to move freely. What's going to happen? It will just go up like this. So you have an overhanging beam now. So your deformed shape will look like that, right? And you know, right here, the magnitude will be equal to 1. And this becomes the influence line of RC, just the shape, okay? And RA, well, for the sake of completion, let's finish it. You allow RA to move freely. So it's going to be quite similar to what you have for RC. Okay, that's going to be a unit load. And this is the influence line of RA, of course. You got the same as mine? No one's answering that. Anyway, we need the quantitative, which means we need the value. Okay, so, well, if you are going to calculate the value, what do? We need the magnitude of the reaction, right? So from this first picture, if you can recall the force method, you can calculate delta B or delta BX for this method, right? So the only way to get RB is by using superposition, okay? And along with when the unit load is right here, that's delta BB, okay? And so I have it here. In order to get the magnitude, you need to use the superposition, right? I hope you can recall your structural analysis number 1, okay? And here, let me try to write here as well. To obtain the magnitude use not superposition. Actually, that's what we call the compatibility and superposition, right? Or the force method. So you see, delta BB is caused by the unit load. So it's delta BB multiplied by the magnitude of RB plus delta BX. This is the displacement where the unit load is there, right? This is the displacement caused by the reaction. This must be equal to 0. So that means my RB is simply minus delta BX over delta BB, okay, which is right here on the note as well. RB would have to be minus delta BX over delta BB. Now, the thing is, that means in order to obtain the magnitude of the influence line here, do we always need to place the unit load at any x location and calculate delta BX? Because delta BB would remain the same, right? Do we have to do that? Yes, we do, and no, we don't. Because a long time ago, there was also the Professor Maxwell who discovered that delta XB here. Remember, delta XB is displacement at X caused by the load at B. This is what we call Maxwell reciprocal theorem. He says delta BX is equal to delta XB. Can you believe that? This is the reason why your matrix is always symmetrical. And instead of calculate, displacement at B by load at any X location, you just place the load at this location and calculate displacement at any X location instead, which is much more convenient. So when we know this, we still have to do a lot of calculations still, but instead of placing the load every time, you can just calculate the displacement at any X location and replace delta BX by delta XB instead to help reduce your workload. Okay. So is there any question? No. Is this too confusing? Maybe it's a bit confusing at first, but I think when you see the examples, things will be crystal clear very quickly, because all we need is the information about the displacement or deflection. And it is not my intention here to test your ability to calculate displacements, because that was in CVE337, right? So that means, say, in this class, the information about displacement will be given to you one way or the other. And once you have the information about displacement, it is your understanding of this concept that matters. It will lead you to say whether or not you can obtain the influence line of the indeterminate structure. Okay? Question, please. Hello. Hey. Hello.
No question, Professor.
No question. Okay. Well, as I couldn't expect this, right? As if I couldn't expect this. Anyway, we started off pretty much at 9:30, and I say this is almost 10:20. So I think before we begin the example, I think it's a high time that we have a break before it. Okay. So let us have a 15-minute break. Okay, I will pause the record. And if you want to talk about anything while I'm still in front of the computer, you can ask me anytime. Okay, but let us have a 15-minute break first.
Professor, could you scroll down a bit? Yeah.
Oh,
want
I changed the
completely-
slide.
yeah.
You mean this one, right?
Yes. No. That
Scroll-
example of deterministic structure.
Which one? This
In the example 5.
in example 5?
Yeah.
Oh, I see.
Example 5. Yes.
This, right?
Yes.
Oh, my handwriting is awful. And is there any part you cannot read?
It's okay. I can read. Yes.
You know, let me fix this because seeing it the second time it's so awful. Okay. All right. So let us have a break then. Okay.
Yes.
But you can still ask me anytime. Okay. I will. Okay, I think the red light is now on, so this is being recorded. So let us jump into the example right away. Okay. This is the first one, the typical indeterminate structure with 1 degree of redundancy. That is the support reaction. Okay. We will try to obtain the influence line for all the reactions VD and MD for the beam as you did see. Okay. So let's say generally we're just going to have to turn this into the determinate structure. And again, my choice would be to turn this into a, what do we call it? Primary structure, right? By removing reaction at B. So this is what I have. Okay. This is my primary. And generally, what I have to do is just I would have to place the unit load at B, and I will try to have to calculate the displacement at every 1.5 meter location. You see here, every 1.5 meter increment of the beam. So generally, would you like me to show the method that I use, or would you like just to get the information? Because I will not ask you to do it in the exam. Let me read class. Hey, please. Would you like to see the method or you don't want to?
I want to see.
You want to see? Yeah, I know, you know, every year someone will always want to see. But so it's not surprising, you know. But I will use, I think the most convenient way to calculate the displacement at each location of this beam is just by using the conjugate beam method. Have you ever heard of it? The conjugate beam method is the method that we put the bending moment diagram of the beam itself on the beam. And so for this, Okay. The when the unit load is here, the bending moment diagram of this beam when the unit load is at B, bending moment diagram looks like that, right? And the moment here is P A B over L. This is A, this is B, and the entire length is L. So the maximum moment is 1, which is P, A is 3, B is 6, and L is 9. So, that is 2. So that means maximum moment here is 2. And this is bending moment diagram. Okay. And it's not just bending moment diagram, it's what we call M over EI diagram. So the magnitude is 2, but it has to be divided by EI. And this is your bending moment diagram. When you put this bending moment diagram on the beam will be called the conjugate beam. Beam with bending moment diagram as its load. Okay, so this beam will have the bending moment diagram as the load. So if this is 2 over EI, the magnitude over here is 1 over EI. And this is 1 over EI. And for conjugate beam, there's a rule that for a conjugate beam, bending moment at any location on a conjugate beam is equal to actual displacement of an actual beam. Meaning, if you want to know the displacement at location number 1, you're just gonna have to calculate the bending moment at location 1 of your conjugate beam. Okay. Hello. Are you with me?
Yes, Ajahn.
Okay,
Yes.
thank you. Thank you very much. Okay. Right. So we're just gonna have to again, execute the free body diagram. The total load here, from this load, you see the total load here is 2 multiplied by 9 divided by 2. So it's 9 over EI, right? And you can, take moment and you see that the reaction here will be equal to 5 over EI. And here is 4 over EI. Cool. Okay. 5 over EI and 4 over EI. It shouldn't be difficult, right? You break the big triangle into 2 small triangles and take moment. So that means the displacement at number 1 here. Okay. Displacement of the actual beam at location number 1 is going to be equal to the moment at location number 1 over conjugate beam. So I put the hyphen on here so that we are talking about the moment of the conjugate beam. Okay. And that means we are going to cut the free body diagram here and take moment here. So that's going to be equal to the reaction But since everything is on 1 over EI term, so I'm just gonna factor it out. Okay, 1 over EI is up front. So this, the reaction is 5 multiplied by the moment arm, which is 1.5, correct? Minus the area of this triangle, which is a half of the height, which is 1. The base is 1.5. And multiplied by the moment arm, which is 0.5, right? And this turns out to be 7.125 over EI. And we can just now, repeat the procedure. Displacement at location B, where we remove our reaction, is going to be moment of a conjugate beam at B, which is equal to 1 over EI. Reaction is 5 multiplied by the moment arm. B, the moment arm is now 3. Minus this triangle, right? Which is a half of the height, which is 2. The base is now 3. And then multiply by the, if the base is 3, the distance to the centroid, here is 1. Okay, so this turns out to be 12 over ER. And let us, try to complete our job. Delta 2, again, this is moment of the conjugate beam at location 2, and the things will repeat themselves. Reaction is 5 multiplied by 4.5 now. And, okay. You know what? It's easier to do it from the right. So let me stop that. For this at location 2, I think I'm gonna take the moment and by looking at the this free body diagram instead. Okay. So it's gonna be the reaction from the right instead of from the left. So this becomes 4 multiplied by the moment arm, which is 4.5, I guess. Minus a half of the height, here should be 1.5. The base is 4.5. And now you should know the moment arm is a third of 4.5, which is 1.5. Okay, this is 12.94 over EI. Okay. Are you bored of this? Would you like me to tell you the numbers right away, or would you like to have it all? Because it's a repetitive. Next is the delta D. Do one more, okay? So it's equal to conjugate beam at the moment of a conjugate beam at D, which is 1 over EI. The reaction is 4. The moment arm is now 3. Minus the load, which is the triangle. The height is 1. the base is 3. So the moment arm of the triangle is 1. This is 10.5 over ER. And the last one, delta 3. It's a similar fashion. It's a moment at 3, and let me give you the number. This is 5.81 over ER. It's similar to what we have done before, and I guess you can do it. Okay. So from this information, we can plot the deformation of our primary structure, right? The structure that we remove RB. Everything okay? So maybe some of you have started already, but let me try to this is A and C, right? Okay, so let's see if from my drawing should be good enough. Let's use different color to differentiate the numbers. Okay, so here is 7. What? 0.125, 12, 12.94, 10.5, and 5.81. Generally, let's say it's not my purpose to measure your ability to calculate displacement. So some kind of information would be given to you either directly by numbers like this or formulas for you to calculate these numbers by yourself. So you can say generally you should start off here with the information of displacement. So now it is your job to know how to turn this information into something that you can use to obtain your inference line. Okay, so now we know that we can say RB is minus, actually, you know what? I'm sorry. It should be the other way around. So let's bear with me a bit. Let's not erase this, but let me try to show you one more thing. Because what we have calculated is the displacement, right? So the correct way to draw, it's just the displacement should be downward. Okay, so the correct drawing should look like this. You know what? That's not very. No, I'll try to do. I always try to draw a very realistic figure so that you have a feeling for it. It's about 1/3, right? And the freehand is something that always helps me. Okay, so what you should have is something like this, minus 7.5. Oh, don't have to be minus, okay? Because we have calculated displacement, so it should look like this. So in fact, this picture is minus displacement, right? And again, but the from the previous hour, which I'm not sure if you have forgotten about it. Maybe you have. The reaction at B is equal to delta Bx over delta Bb, right? But with the minus sign, so this is the picture that you should use. And this is the picture that is going to be the shape of your influence line. This, the picture that I just drew, this is the displacement. Or what displacement should look like, right? So when we multiply the displacement with the minus sign, it's like we flip the graph. And so this flipped graph will be the shape of the influence line of reaction at B, which you are going to get. Okay, so which one is delta BB, ladies and gentlemen? Which one is delta BB? Where is B?
In the middle?
Well, in this case, it's not in the middle, right? See? B is here at 1/3, okay? So this is where B is, right? Thank you for answering. So we divide every number here by delta BB, which is 12. And that is exactly when you're going to get the influence line of RB. So from here, I divide everything that I have by 12. That's bad. Let me do it again. Still pretty bad. Let's do it from the other side. Okay, better. Right. So this is can read my handwriting. Oh man, this is tough. I think I'm not sure if it's you know what? Let's recalculate. It's 7.125 divided by 12. That's 0.59. Okay. So this is 0.59. Is 7.125 divided by 12. And so this is 1, right? You know what? My drawing is really ugly and doesn't represent what it should look like. Let me try again. Something like this. Okay, now that looks better. Okay, this is 0.59, which comes from 7.125 divided by 12. And 12 divided by 12, that is 1. Because that's where B is, right? And the value of the influence line at the reaction itself should be equal to 1. And here is 12.94 divided by 12, so it's slightly over 1. So you see, the location that gives the maximum RB is not where the unit load lands on B itself. That's the indeterminate structure to you. This is 0.88, and this is 0.48. Oh, it doesn't look like 8, man. So this is the influence line of reaction at B. We are finally here. Is there any question?
Professor,
Yes.
in the previous page, can you scroll up a little bit?
Sounds like David.
A little bit more, yeah.
Okay.
Where does the 2 over EI come from?
2 over. Oh, that's the here. The moment calculated by using PAB over L. P is 1, A is 3, B is 6, and L is 9. So the maximum moment of this beam with the unit load is 2. And in conjugate beam, we need to use the moment divided by EI diagram, or we call it M over EI diagram. So once I have 2 from this calculation, I divide it by EI.
Oh, thank you, Professor.
Cheers. Okay. So is there anything else? And once we have reached this point, we should know that we should know that we have, or you should know that you have the one reaction solved. So that means now we have turned this structure into a determinate structure because you now know the magnitude of reaction at B whenever the unit load is, right? At every 1.5 meter increments. So that means to obtain, say, reactions at A or at C or VD and MD, you are now calculating a determinate structure, correct? So what do you think we should do? Okay. RA. I'll try to, use the left side, maybe because we are on the different page now. I don't have to draw, say I'm directly underneath those. So let me try to move this to the left a bit to create the space on the right. So now RA. Remember that now you know RB. So how do you obtain RA? You take sigma mz equal to 0, right? Isn't that the most sensible thing? Now it's a game of free body diagram. So when you take sigma mz equal to 0, you have, say, what's your beam looks like. So let me, draw it somewhere here. Okay, remember that you know all RBs, right? Now you want RA, and you have the unit load at the location X. So this becomes the total length of the beam from A to C is 9. So this is 9 minus X, right? We take moment at C. So RA multiplied by 9 plus RB multiplied by 6 minus unit load multiplied by 9 minus X equal to 0. That will be your equation. Now you keep plugging in. Let's say if your X is equal to 1.5, for example, you know your RB is 0.59, right? So RA, what's going to be? So and so. If X is equal to 3, your RB is equal to 1, what's going to be Rx? You keep doing that, you will obtain the free body diagram that looks like this. I'm sorry, I mean the influence line. that looks like this. Been saying free body diagram too many times, right? Okay, this is gonna be quite difficult to draw, but I'll try. You know, this has to be equal to 1. Oops, look pretty bad. You know what? Pretty crooked. Okay, but at B, RA would have to be 0, right? And I'll do my best. Okay, oops. Yeah. It will look something like this. Okay. And if you keep plugging the numbers, you will obtain the numbers that look like this. This, of course, is 1. This is the inference line of A. This at the location 1.5. This is, can't read my handwriting again. 0.44, I guess. This has to be 0 because that's where support B is. This is minus 0.22. This is minus 0.25. And this is minus 0.16, roughly. Okay. See, the point is just to solve one unknown. And so your entire structure becomes determinate. And once we have that, the rest is just, again, playing around with free body diagram and equilibrium. And now you have RB and now you have RA. What do we do with RC? Just leave some space. The easiest way to obtain RC, just, you know, it is going to be equal to 1 minus RA minus RB, right? Because now you have both RA and RB. So why don't we take advantage of sigma y equal to 0? And with the similar approach, you know, let's say when X is equal to 1.5, you know, RB is 0.59. RA is what? Sorry, 0.44, right? And so on and so forth. So you're gonna get RC that looks like this. And you know, at A, RC has to be 0 because the force is at A. So RC has to be 0, and at B as well. So you will guess RC will look like this. Okay. And here is minus 0.031. And here is 0.14. Here is 0.38. And here is 0.67. Okay. Now it's going to be a bit more fun. You guys catching up? I guess that's a yes.
Yes.
Yes, okay, good. Now, it's time for us to get into a more, say, slightly more troublesome design functions such as a shear and moment at D. So now we're gonna have to do some free body diagram. Okay. When I cut the free body diagram at D, Okay. We have A and we have B, right? Excuse me. This is A, this is B, and that's where D is. D, right? Remember now that we have all the values of all the reactions. So first free body diagram. Your unit load is here. Correct? So when you look at this free body diagram, you can use your sigma Fy equal to 0 to write your VD. VD is going to be equal to RA plus RB minus 1. Correct? Do you agree? Nobody agrees with me.
Yes, Ajahn.
Yeah, it's pretty obvious, isn't it? But the catch is that this free body diagram and this equation valids only when this unit load is on this free body diagram, correct? Which means this equation is valid only when x is from 0 to 6. Correct? But once this load, once unit load leaves the free body diagram, well, the free body diagram still works, but the equation would change because you no longer have the unit load there. So your VD is going to be equal to RA plus RB. When X is from 6 to 9. Right? See, this is the time to show your truthfulness or your loyalty to free body diagram. Because I can easily say, you know, if my unit load travels beyond this point, somehow I couldn't include this. Let me try again. I'm gonna drag the beam with it. Okay. If my unit load travels beyond this point, if the free body diagram is correct, this one will have to remain correct, right? Even though there is no unit load on it, but the unit load will not be on it when it travels beyond point D, which means your X is down beyond 6. So the second equation will be in play when your unit load travels beyond point D. So this free body diagram remains correct regardless of where the unit load is, but the equation will have to be corresponding to the unit load as well, right? Any question? So, you know, in a nutshell, the influence line will look like this. Okay. This is 0.031. This is 0.14 minus 0.14. This is minus 0.375. This is 0.625. It has to be 1, right? And this is this is 0.328. Okay, and this is your influence line of shear at D. Okay, is there any question? Should be on the half. Okay, question. Hello. Hello. No question, I suppose. So the last thing before we take another break is to get rid of the last remnant, which is moment, right? Oh, we have another free page. So again, using the same free body diagram. Oh, I should say VD here, right? So now MD. Again, we use the same free body diagram. And now again, we have the values of RA and RB. We just take moment at D, right? So we can write the moment at D equation very easily. That's going to be RA multiplied by 6 plus RB multiplied by 3. But don't forget that we also have the unit load. Minus the unit load multiply. Now we need the distance, right? If this is X, this is going to be 6 minus X. 6 is where D is, right? But you know, with the similar thing. So you would recognize right away that this moment equation is only valid when X is from 0 to 6, because that's when you have the unit load on your free body diagram, right? And once your unit load leaves, I think my handwriting just starts to go down. Leave the free body diagram, your moment equation would just be equal to RA multiplied by 6 plus RB multiplied by 3 without the presence of a unit load anymore. And this equation valids from X equal to X. You know what? Let's do it again. Six up to 9. Okay. Any question? So you see, it all comes down to free body diagram and equilibrium again. We are not getting away from that, right? Hello. Okay, if there is any question, let us finish the job by drawing the influence line of MD right away. Okay. Looks like that. Well, you would expect moment to be 0 when the load is at the support, right? And rightly so. And you should know for the indeterminate structure, the influence lines are always a curve, okay? No straight line. And that's the shape. Right here is minus 0.118. This is 0, of course. Right here is plan C. 0.312. Here is 1.182. And right here is, oh, geez, 0.582. And that is the influence line of MD, okay, obtained by using the equations which come through the free body diagram. Question, please. Are you working on this? Can I scroll back up a little bit? Okay. Well, let me scroll back up a little bit to recap what we have done. See, the whole fundamental key to this is how to turn the information here, which is the displacement, into the first influence line. So the most important thing is just to know how to turn the displacement that we calculate, you know, here into the influence line of the first reaction. So once you have obtained the first influence line of any reaction, it means you have now turned your structure into a determinate structure, because this is 1 degree of redundancy, correct? So once you have obtained one influence line of any reaction, the rest can be obtained just by looking at your free body diagram, write your equilibrium equations, and use the values obtained from the first step to obtain, you know, the remaining numbers. Okay, so say you have any question. Hello.
Professor, can you go to the last part?
Last part here.
Yeah. For MD, why is only OA times 6 plus OB times 3?
Yes, because you mean this equation, correct?
Yes.
Well, this is correct because this is the equation where your unit load has gone beyond this free body diagram. So let's say it would be less confusing if we try to draw another free body diagram for this, because this second equation is for this free body diagram. Right? This is for shear. Look at this. This free body diagram, regardless of where the unit load is, it has to always be correct, right? If your unit load is outside this free body diagram, say here, and I want to determine VD by using this free body diagram? Can I do that? Yes or no? Can I use this free body diagram to obtain VD even though there is no unit load on it? Can I do that?
Yes.
Yes, I can. So the equation becomes this one. And likewise with the moment. I can also use this free body diagram to obtain MD. Oops. Not to write R. I can use this free body diagram to obtain MD, but the equation will have to be this one. Right? Okay. Geez, stop something. It's good that you asked, you know. Okay. Is there any more questions regarding this problem? I guess that means no. We have another example before the class is over. Now it's another 1 degree of redundancy structure. So it's a prop cantilever. Okay. So let us take another break before we resume the class. So this is going to be the last mini break for CVE338, right? Because the next session will be the end game. We can say that. Okay. So you want 10-minute or 15-minute break? Because we're going to finish it in time, I'm sure. 10 or 15?
15.
Okay, 15 it is then.
See you at 35, Professor.
Yeah, see you at 35. Hey, what's this? Okay, right. I have resumed the recording. I think now the record is on. So let us proceed with the last problem of structural analysis number 2 of this semester. Okay. Now, because I said that we will only limit the influence line of the indeterminate structure to 1 degree of redundancy. This problem should cover another remaining possible case. This is a 1 degree of redundancy of a prop cantilever. Okay. And again, when I see something like this, I prefer to remove the reaction at C. So my primary structure will become something like this. Okay. And when I apply the unit load here, my bending moment diagram is going to look like this. I believe the distance is 6 meters. So the M over EI diagram, this is minus 6 over EI, right? And now the best way to calculate the displacement at any location is not to use the conjugate beam, but to use the moment area method, if you can recall that, because this is a cantilever beam. Okay, and say for a little refreshment of memory, let's say we are looking to calculate the displacement at C, right? So let me call that point C, and the displacement at C is going to be equal to TCA. That's point A, right? And if you can recall, TCA is the moment of the bending moment diagram between point A and C with respect to point C. Okay. So right here, it's going to be quicker. Delta C is TCA, and it's the entire triangle, which is going to be equal to minus a half of the height, which is 6 over EI diagram. The base is 6 meters. And the moment arm with respect to point C, so it is this, right? 2/3. So it's 4 meters. The moment arm is 4 meters. And here it is equal to minus 72 over EI. Next is delta C when the load is at location number 2. So delta 2 is going to be T2A. It's kind of strange to call it like that. But you know what? My handwriting is going bad again. Let me do it again. Not T. Delta 2. This is going to be a little bit troublesome because, say, this is going to be the area of the moment diagram between 2 to A, which is, say it's a trapezoidal. It's a trapezoid. So instead of doing that, how do I do that? Okay. when you see it's a trapezoid, right? So when you have to calculate this, we have to exclude this part from our calculation, right? And the area becomes this purple one. So the easiest way to take a moment of this with respect to point C, just to break this into a one rectangle and one triangle, okay? And this is going to be I didn't do it like that. What do I do? I think it should be the same, but one moment. Okay. I don't know what I did. This is weird. Hang on a minute, okay? Sorry for this. I have done this long time ago, and I believe what I did long time ago was correct, but I don't recall what I did. It's 4.5. No idea, but this this idea should be correct, but it's not what I did before. So let's say, but this is going to be difficult. The idea of what I did before seems simpler, but I cannot decode it. What is that? Anyway, you know what? Let's skip this, okay? And if you're curious about this, I can try to decode what I did before and just post it on the group later. To try to dwell on this would take too much time. So let us get the numbers right away. This is minus 45.56 over EI. You can just use the one rectangle and one triangle to get this, or the method that I use, which I don't recall how I did it, but give me some minutes afterwards. I may recall something. But for now, let's just try to save some time and go ahead with the numbers. Okay, the displacement at B, of course, this is T BA, and this is going to be equal to minus 22.5 over EI delta 1, that's minus 6.19 over EI, and then delta D, last one, is what is this? It's very interesting because you must know that at point D, before we go over, point D here is after the load itself, right? So this would have to be the straight line. And simply it is this, it's T, let me show you, it's T DA, which is essentially this triangle again. 6 over EI as the height, multiplied by the base. But now, oh, sorry. The moment arm becomes 4 plus 1.5. And you would expect this to be a straight line. And this is 99 over EI. And so if I plot these values, the displacement will look like this. It will be a curve up until point C. And this is a straight line. Because there's no node after it, okay? And here is minus 72 over EI. Here is minus 99 over EI. Here is minus 6.19 over EI. Here is minus 22.5 over EI. And here is the minus 45.56 over EI. And again, we use the compatibility to obtain RC, which means we're going to have to divide everything by displacement at C, right? So the key is to know which displacement you're going to have to use. And this time, because we remove RC, so we're going to have to divide everything by displacement at C, which is 72. And remember, it's a minus sign, so we flip this. So that means the influence, oh, you know what, I don't have to draw this, right? The influence line of RC will look like this. And it becomes straight line in the last part. And so this is, hang on. This is, the first point is 6.19 divided by 72, right? So it is 0.086. The second is 0.312. The third is 0.633. The fourth one is of course 1. And the last one is 1.375. So this becomes, remember that this is straight. And this is the influence line of RC. Okay. Any question up to this point? Quiet. Anyway, so again, once we have obtained one reaction, we have successfully turned this structure into a determinate one. So the rest would just be piece of cake. Okay. You can use this free body diagram. Now you have the RC and you have the unit load. You don't want to know RA, so you can just take moment a day. sigma MA equal to 0, you will have MA equals RC multiplied by 6 minus 1 multiplied by 6 minus x. Oh, sorry, we take moment at A, right? So, excuse me. This is x. X is there. Okay, so doing that will give you the moment at A in no time. And you're gonna have the inference line looks like this. No. You know what? Wow. Looks good. The inference line should look like that. And this is the inference line of moment a day, of course. Calculating the values from this equation, you should have the values here is equal to minus 0.984. Here is minus 0.125. This is minus 0.702. At C, it has to be 0 because that's when the load is at C. You cannot have moment, right? And this is 0.75. And don't forget that this is straight line. Okay. And you know the easiest thing. The next is force RA. So you have RC. We have the support there. Sigma Fy equal to 0. Give you RA is equal to 1 minus RC, right? This is the easiest thing in the world. So with the same approach, we can now obtain the inference line very easily. Inference line of RA just gonna look like hold on. Seem to be on. Oh, you know what? Okay. Right. Okay. Ooh. Look about this. Okay, and of course this has to be equal to 1. Right here is 0.914. Here is 0.688. Wow, man. Oops, sorry. It's me, right. 0.688. Here is 0.367. Here's 0, of course. And then the last value is minus 0.375. Okay. And the rest is just, you know, playing the same game. With one trick question, That is. Are you still with me? Am I going too quickly? MA is done, I is done. MC, you know? MC, it has nothing to do with this being indeterminate or not, because the only way that you can have moment at C is when your load is somewhere around here, right? If you can recall what you've done before. So MC would just, you know, looks like the influence line of your you have done before. It's going to look like this. Because the only way you can have moment at C is when your load is out beyond point C. And this magnitude is going to be just, you know, when you place the unit load here at point D. And the moment at C will have to be this distance multiplied by the unit load. So it's minus 1.5, yes. Let me erase this. Right, will cause confusion. Right, has nothing to do with this being indeterminate or anything. Next is say this is for MA. This is for RA, right? MC. Now is what? VB, right? So in similar fashion to the previous problem, we just cut the free body diagram, right? At B. When I cut the free body diagram at B, again, I will have two cases. That is, when the unit load is on this free body diagram and when it is not. So when the unit load is on this free body diagram, my VB is going to be equal to RA minus 1, which is the unit load, right? But this will be valid from 0. Sorry, it's the wrong direction, right? X0 to 3. Because B is when X is equal to 3, right? And our VB is going to be equal to, oops, sorry, to just RA. When again, the unit load leaves the free body diagram, which is when X becomes greater than 3. Okay. And as a result, we will have the influence line that looks like this. Point B is right around here. You know, can I lock it? Is it so? Okay. All right. Gonna look like that. And the numbers, this is 0.086. This is minus 0.312. This is 0.688. What? Right. This is drawn incorrectly. Excuse me. It has to be 0 at the support, right? Got that. Okay. And here is Henry 0.367. This is 0, of course, and right here is minus 0.375. So this is the inference line of VB. Okay, don't forget that again, this is straight line. Okay, lastly, moment at B. Same trick, you know, same free body diagram, but this time we focus on the moment. And again, there will be two equations when the unit load is on your free body and when it isn't. But don't forget that you also have MA. Okay, this is MB. So MA, sorry, MB, I mean, will be equal to minus MA plus RA multiplied by, what's the distance? 3, right? And this time we take moment at B, so here we'll have to minus the unit load multiplied by 3 minus X. Okay, because that's the distance. 3 minus X. And this is valid when X is between 0 and 3. Of course, it is equal to minus MA plus RA multiplied by 3 once the unit load leaves the free body diagram. So this is from 3. Oh man. You know what? I can just move this up a bit because it is so tiny little thing and I want it to be on. Damn it. I want it to be on the same page.
I know you are. How did we? How they go?
Are you talking to me? Perhaps not.
May I want?
That's not directed at me, right? Ooh, it's pretty windy around here. Okay. All right. This is from 3 to 9. 7.5, right? It's it. Yeah, not 9. Like that's from the previous problem. So let me, and this is not beautiful. Let's rewrite again. 3 x 7.5, and this should be 7.5 as well. Okay, so that's that. And yep, it's time to deliver final answer. Okay, it's a bit too long. Anyway, around this, and it's gonna look like this. Curving up at B and curving down, and this again the straight line. Okay. This is the inference line of MB, and this is 0.258. This is about 0.938. This is 0.4. This is 0, of course, and the last one is 0.375. Okay. All right. So that's it. We have like 15 minutes left. So is there anything unclear? I'll give you a few minutes to wrap this up, and then I'll tell you a few things about this. Okay. You know what? I figured out what I did with the triangle thing, and go back and tell you the details about it now if you want. I thought I did that, but I wasn't sure, but now I'm sure. Yeah, sometime I was quite smart back then. Okay, are you still working on this? Maybe. Okay. Are you ready to listen, or are you guys still taking some notes? Hey,
Ready, Cop.
ready. Okay. So first and foremost, the most important thing is you need to be able to figure out, because generally I am not asking you to calculate displacements. So displacements will be given in some form, either the numbers like you see here, or the formula to create them. So you must be able to find the relationship between the information about the displacements that you are given, and try to turn it into, the influence line of your redundant. Okay, for example, if I give you this information right away, say I give you information of the displacement of this information would be information about the displacement of this beam under this load, correct? Say if this information is given to you, I say, okay, the displacement of this beam under the unit load or under any load at this location can be given by this. Use this information to obtain the influence line of this. You must know that this information must be used to determine RC. This is the knowledge that you must have. Or if we go back to look at this problem, and I say, okay, this information is given to you. This is the information of the displacement of a simple beam underneath the load at location B. If this information is given to you, use this information to calculate all this hullabaloo, So you must know that this information must be used to obtain inference line of RB. And it's very easy because you know this is the displacement at B. So you divide everything by 12, you get the information of inference line at for RB right away. This is the knowledge that you must have. And likewise, if this information is given to you, you divide everything by 72, you get the inference line of RC right away. Okay. That is the key to doing this. And it's pretty straightforward because once you get the inference line of one redundant, everything becomes, you know, say determinate. And one more thing I like to tell you is that I divide this picture into two triangles, not this one. Two triangles is easier to deal with. Instead of one rectangle and one triangle, you divide this into a picture like this. So now you got two triangles, right? The first one, this one has a base of 4.5, but the centroid is at 1/3. This one also has a base of 4.5, but centroid is 1.5 from point C. This triangle, same base, but the centroid is 1.5 meter from point A. Okay, so that is the idea. Okay, and I can squeeze this in here as a delta 2 by using these two triangles. It's going to be equal to minus a half of the height, which is 6 over EI. Base is 4.5. This is the big one, right? And the distance here is 2/3 of 4.5 minus another one, the small one on top. The height is right here, the height is 1.5 over EI. The base is the same. And the distance to centroid is now 1/3 of 4.5. Okay, same thing. And it gives you this number. Okay, so now I don't owe you anything. Okay. Is there any question? Hello? Anything unclear?
Crystal clear, Professor.
Crystal clear. Excellent. So if there is any question, I'd like to pause the record for the time being so it doesn't get too long.